Hello students, so welcome back in our remote sensing series, lecture number 3. Just 1 second. So in the previous lecture, we learned that every object of absolute zero temperature emits energy. But an important question is, do all objects emit the same amount of energy? So no. The black body emits maximum possible energy while natural object emits less. So to understand this difference, we need to learn important properties such as emissivity, transmissivity, reflectivity, absorptivity, Kirchhoff's law. Okay, so in this lecture we discuss one by one in very simple language. So let's start with spectral emissivity. So uh, open your book and let's imagine. So imagine you keep a black t-shirt and a white t-shirt in the sun. And after 1 hour both become hot. Now bring them into shade. Which one cool down faster? Usually the black t-shirt. Why? Because it's not only absorbs more heat, it also emits more heat. So this ability to emit energy is called emissivity. So, what is basic definition? Every object above 0 Kelvin. What is 0 Kelvin? Absolute temperature. Absolute temperature in degrees Celsius minus 273.15 degrees Celsius. So, emits electromagnetic radiation. Some object emits a lot of energy and some emits very small. So, what is emissivity? Emissivity tells us how efficiently an object emits radiation compared to a perfect black body at the same temperature. So always we take the definition in reference to the black body. Why? Because black body is an ideal case scenario which is have maximum emissivity. Okay. So what is in mathematical terms? M lambda t upon m lambda bbt, where m lambda bbt is by the black body. What is bb? Black body. Okay. So if we understand formula in simple way, so suppose you have 10 suppose at the 10 micrometer wavelength, suppose at 10 micrometer wavelength, black body emits 500 watt per meter square per micrometer energy, and a granite body emits 450. So what is the emissivity? Epsilon equal to 450 upon 500 equal to 0.9. So this means granite emits 90% as efficiently as a black body. So this is meaning of emissivity. In physical term, emissivity is not the amount of energy, it is efficiency of emission. So think of it like an exam. So a student scored 90 out of 100. So his efficiency is 90%. This is some way similar about your percentile as you get in gate exam or net exam. So similarly like that, a material emitted 90 unit compared to a black body's 100 unit has an emissivity 0.9. Okay, and next term is spectral emissivity. So what is spectral emissivity? In the term emissivity we have lambda, epsilon lambda. So what is lambda? Lambda is wavelength. So in spectral emissivity or normal emissivity we have epsilon lambda, where lambda is wavelength. This is include, this means emissivity may change with the wavelength. So for example, at 5 micron a mineral may have emissivity 0.85. So at 10 micron it may become 0.95. Therefore emissivity is often wavelength dependent. So this is an important point, that spectral emissivity is sorry, wavelength dependent. Next, there is in term gray body and selective radiator. What is gray body? So if emissivity is almost constant for all wavelength, so we tell that body gray body. Gray body, if emissivity changes with wavelength, and selective radiators when most natural materials are selective radiator. So if emissivity change with wavelength, we call that body gray body, or if selective radiator, so we call sorry, most of the natural object which present in the on earth is known as selective radiator. So this is why different materials have different electric spectral signatures. In remote sensing, this is where the concept become important. So thermal infrared satellites such as Landsat, TIR, ASTR measure radiation emitted by Earth's surface. So however they measure radiation or radiance, not temperature directly. What is radiance? We studied in previous lectures. So, to calculate the actual surface temperature, we must know the surface emissivity. If emissivity is ignored, surface temperature will be incorrect and land surface temperature estimate become inaccurate. This is why emissivity correction is an essential step in thermal remote sensing. So, for exam, what you have to remember, emissivity range from 0 to 1, black body have emissivity equal to 1, and natural object have emissivity less than 1. Good emitters are generally good observers. That is also Kirchhoff's law, which we discuss later. So what is advanced inside? Emissivity dependent on several factors such as wavelength, surface roughness, material composition, moisture content, temperature, weaving angle. So, for example, a dry soil and a wet soil at the same temperature can have different emissivity. Okay, so I think now emissivity is clear. So, we read from book. So it is defined as the ratio of spectral radiance emitted m lambda from an object at temperature T to the radiant existence from a black body at that time temperatures m lambda bbt. So what is the emissivity? Spectral radiant existence for an object and with the reference with black body. In other words, the emissivity describes how well an object radiates energy compared to the perfect black body radiator, and it is unitless. Why unitless? Because both have same unit values with a range 0 to 1. What is emissivity range? 0 to 1. Object whose emissivity is approximately constant with wavelength are referred to as gray body. What is gray body? When emissivity is constant with the wavelength called as gray body, while objects with spectrally varying emissivity are called selective radiator. If constant gray body, if select spectrally variable, that is called as selective radiators. So a gray body has an emissivity epsilon less than 1 but constant at all wavelength, and natural material don't behave like gray body. Why? Because natural material change their emissivity with the change in wavelength. Emissivity, absorptivity, reflectivity, and transmissivity are fundamental properties of matter. So, these are fundamental properties of matter. Next, we discuss about transmissivity. So, let's start with a story. Imagine you are standing near a window on a sunny day. So, sunlight falls on the glass, and what happened? Some sunlight passes through the glass and enters the room. Some is reflected back, and some absorbed by glass. The This is so much. Okay, this is window, and you are standing behind the window. Okay, so when some sunlight get into this window, what happened? Okay, so some sunlight passed through the glass and enter the room, which is shown by the test line, and some are reflected back. So these are reflected waves, and some absorbed by glass. This don't show exit point, so this is absorbed by glass. So the amount of sunlight that passes through the glass is called transmissivity. This is called transmissivity. What is emitted called emissivity, and what is transfer is called transmissivity in simple language or in layman language. Okay. So, what is the basic definition of transmissivity? Transmissivity is the ability of a material to allow electromagnetic radiation to pass through it. In simple words, it tells us how transparent a material is to radiation. So, if the more radiation passes through, the material is has high transmissivity, and if very little or no radiation pass through, it has low transmissivity. What is the mathematical definition? Lambda t equal to m tau upon mi. This is dimensionless also because both are the same dimensions. So, what is lambda t? Spectral transmittance, m tau spectral existence, and ei spectral iridescence. What is spectral existence and iridescence? We discussed in previous class, so I don't repeat that. So transmissive. So understand the formula. Suppose you have 100 watt per meter square of solar radiation. Okay. Solar radiation falls on a glass sheet. Out of this, 75 watt per meter square pass through. So what is the tau? Tau is 75 upon 100 equal to 0.75. This means 75% of the radiation is transmitted. Physical meaning, how we think. So think the transmissivity as permission to pass. And if a material allow most radiation to pass, transmissivity is high. If the body radiation blocks radiation, its transmissivity is low. If anybody hold or reflect back more radiation, that is transmissivity value low. So high transmissivity objects are clean glasses, pure water for visible light, clear plastic. These material allow most of the visible light to pass through, and medium transmissivity frosted glass, thin clouds, dirty window glass, only parts of some radiation pass through, and low transmissivity, brick wall, metal plates, rock, wood, almost no visible light pass through these material. What is the relationship between wavelength and transmissivity? One very important point is that transmissivity depends on the wavelength. So, for example, if glass is transparent to visible light but blocks much of the thermal infrared radiation, so similarly, the Earth atmosphere allows visible light to pass easily but absorb many infrared wavelength due to gases like water vapor and carbon dioxide. This is why satellites use atmospheric windows for remote sensing. Okay, so what is transmissivity's application in remote sensing? Transmittivity is extremely important in remote sensing. Why? Because radiation must travel through the atmosphere before reaching the satellite sensor. Because has satellite sensor tech energy? Energy, so sun rays are coming to the earth surface and reflected back to sensor. This is satellite, and satellite record this. So the atmosphere does not transmit all wavelength equally. Some wavelengths are absorbed by atmosphere gases while other pass through almost completely. These wavelength ranges are called atmospheric wavelength. For example, visual window approximately 0.4 to 0.7 micrometer, and thermal infrared window approximately 8 to 14 micrometer. Remote sensing satellites are designed to collect data mainly in these atmospheric windows because their transmissivity is highest. So, what you have to remember for exam, transmissivity range from 0 to 1, tau equal to 1, completely transparent material, tau equal to 0, completely opaque material. It depends on wavelength, it is dimensionless quantity. Okay. And what is atmospheric transmissivity? How much radiation passes through the atmosphere? And what is material transmissivity? How much radiation passes through a material like glass, water, or plastic? So, when satellite measures Earth's surface temperature or reflectance, scientists apply atmospheric correction to remove effect of atmospheric transmissivity. Okay. So, what is transmissivity? If we take a quick revision. So what is transmissivity? Transmissivity is ability of a material to allow radiation to pass through it. Formula: tau equal to transmitted radiation upon incident radiation. Range 0 to 1. Tau high, clear or glass like clear water or glass like substance, and for low, rock or metal brick. Remote sensing importance: helps identify atmospheric windows and essential for atmospheric correction before applying to satellite images. Okay, now we read from book. So it is the ability of material to allow the flux to propagate through it. The spectral transmittance tau is simply the ratio of spectral existence. Spectral existence means, in simple language, transmitted radiation, and what is back to sample spectral iridescence or incident radiation, call that, on the front of the sample. What is tau lambda? There is lambda, so dependent on wavelength, m tau upon ei. Both have same dimension, so this is dimensionless property. Next property that we have reflectivity. Emissivity: emit radiation. Transmittivity: transmit the radiation. And reflectivity. So what is reflectivity? Let's start with this also with a story. So imagine you are standing outside a sunny day and you have two objects in your hand: a mirror, or second one is a black cloth. When sunlight falls on them, so the mirror sends most of the light back towards your eyes, and black cloth reflect very little light. Why? Because different material have different ability to reflect radiation. So this property is called reflectivity. So what is the basic definition of reflectivity? Reflectivity is the ability of a material to reflect or bounce back the incoming atmospheric radiation or electromagnetic radiation. So in simple words, reflectivity tells us how much incident radiation is returned from the sun. The higher the reflectivity, the brighter the object appears. What is the mathematical definition? R equal to mr upon ei. This is also dimensionless. And what is mr? Mr is the existence and mi is the iridescence. Same as this. Transmissivity and reflectivity. So mr reflected radiation and ei incident radiation. It is a ratio, so it has no unit because both have same unit. So suppose, same example, if 100 watt per meter square sunlight falls on a snow covered area, and if 80 watt per meter square reflected back, so what is the reflectance? 80 upon 100 equal to 0.8. This means the snow reflects 80% of incoming energy. So if high reflectivity, that means most radiation is reflected. High reflectivity means most radiation is reflected, and low reflectivity means most radiation is absorbed. Okay. In real life example, if we take, so mirror have high reflectivity, fresh snow high reflectivity, white paint high reflectivity, clouds high reflectivity. And what about medium reflectivity? Dry soil, sand, concrete. Low reflectivity: coal, asphalt road, dense forest, black cloth. These surface absorbs most of the radiation and therefore look dark. Or reflectivity and surface color. So generally light colored surface have high reflectivity and dark colored surface have low reflectivity. So however, color is not the true factor. Reflectivity also depends on surface roughness, moisture content, wavelength, material composition, etc. So for example, white soil reflect less radiation than dry soil because water absorb more energy. And reflectivity and wavelength relationship. So reflectivity changes with wavelength. For example, if healthy wavelength reflects very little blue and red light because chlorophyll absorbed it, and a large amount of NIR radiation due to the internal structure of leaves. We discussed in NPYQ about NIR use in vegetation mapping. So remote sensing application. This is one of the most important concept in remote sensing. Satellite sensors do not see objects directly. They record the radiation reflected from Earth's surface, and every mineral reflects radiation differently, create a unique spectral signature. For example, water very low reflectance in NIR, and healthy vegetation very high reflectance in NIR. Dry soil, moderate reflectance, snow has high reflectance in visual wavelength. So using these satellite can identify forest, river, desert, crop, glacier. Even every minerals have its own spectral signature. So each material reflects electromagnetic radiation differently across different wavelengths. So if we plot reflectance on Y like that, if we plot reflectance in Y and wavelength on X, we get an spectral reflectance. Spectral reflectance is something like that curve. The curve act like a fingerprint. For example, we have a distinct fingerprint for every human being. That like every mineral have distinct spectral signature. So this curve like fingerprint for that material. Remote sensing scientists use this spectral signature to identify and classify land cover types. What you have to remember for exams: reflectivity range for 0 to 1, high reflectivity bright surface, low reflectivity dark surface. It depends on wavelength and surface property. Reflectivity is the foundation of optical remote sensing. If we take a quick revision, so reflectivity, ability of a material to reflect incoming radiation. Formula: reflected radiation upon incident radiation. Value range from 0 to 1, high reflectivity snow, mirror, cloud. Low reflectivity coal, water. Water have low reflectivity in NIR region. And asphalt. Remote sensing importance is satellite identify Earth's feature by measuring the reflected radiation from different surface. Okay, excellent. Now it is the ability of a material to turn incident flux back into the hemisphere about the material. Incoming radiation reflected back to the hemisphere. Reflectance can be expressed as the ratio of existence in front of sample to the incident onto the front of the sample. I hope these three properties are now you understand properly. Next is absorptivity. So emit, transmitted, reflected, absorbed. It is the ability. Okay, let's first discuss with a story and then I tell about this. So I drink water, then I discuss. Okay, so welcome back. We talk about absorptivity in a story manner. So imagine you are walking outside on a hot summer afternoon. You touch two cars parked in the sun, or in the sunny over at the afternoon, more precisely. So a black car and a white car. A black car feels much hotter. Why? Because the black car absorbs more solar energy while the white car reflects more energy. So this ability to absorb radiation is called absorptivity. So what is the basic definition of absorptivity? It is the ability of a material to absorb incoming radiation and convert it into another form of energy, usually heat. So absorptivity tells us how much of the incoming radiation is absorbed by a material. The more energy a material absorbs, the hotter it becomes. What is the mathematical definition? Same as above. Alpha equal to m alpha upon ai. What is the m alpha? Absorptance alpha can be expressed as the ratio of flux per unit area incident on a surface that is converted to another form of energy. m alpha, which is absorbed radiation in simple words, and iridescence. So alpha equal to m upon ei. Absorptivity also don't have any unit. And same example, if 100 watt per meter square sunlight fall on the road and 85 watt per meter square is absorbed, so what is the alpha? 0.85. That means road absorb 85% of incoming radiation. If high absorptivity, more energy absorbed and surface become more hot, and low absorptivity, less energy absorbed and surface remains cooler. So what is the real life example? High absorptivity, black cloth, coal, asphalt road, dense forest. These materials absorb most of the incoming radiation. And low absorptivity, fresh snow, white paint, mirror, polished aluminum. What happens after absorption? Most important question. So absorbed energy does not disappear. It converts into heat energy, thermal energy. As the object's temperature increases, it starts emitting thermal radiation. This connects directly to the Kirchhoff law. What we read in 11, 12 physics or chemistry, energy is not destroyed, not generated. It only transfer its state. So that rule also work here, that energy don't be destroyed. That energy which is kept from the environment transferred or modify itself in the form of heat. Okay, so what is the relation with absorptivity and wavelength? Like reflectivity, transmissivity, absorptivity also change with wavelengths. For example, a leaf absorbs blue light, red light. So because chlorophyll use these wavelength for photosynthesis, but it absorbs much less NIR radiation. So that's why healthy vegetation appears green and reflects strongly in NIR. What is remote sensing application? Absorptivity is very important in thermal remote sensing. The temperature on Earth's surface depends on how much solar radiation it absorbs. For example, asphalt road absorbs large amount of solar energy and become very hot. Snow absorbs little amount of energy and remains relatively cool. Water absorbs energy differently and heat up more slowly than lands. The difference creates surface temperature variation which thermal sensor detect. So the amount of energy absorbed depends on wavelength, surface color, surface roughness, moisture content, material composition, and most importantly, angle of incoming sunlight. So, for example, you have to remember absorptivity range 0 to 1, alpha equal to 1 perfect absorber, that is black body, and alpha less than 1 natural material. High absorptivity means higher heating of the surface. If we take quick revision, so ability, what is absorptivity? Ability of a material to absorb incoming radiation. What is the formula? Alpha equal to absorbed radiation upon incident radiation, and range from 0 to 1. What is high absorptivity materials? Coal, black cloth, asphalt. And what is low absorptivity material? Snow, white paint, mirror. Remote sensing importance, control surface heating, and fundamental of thermal infrared remote sensing. Okay, so this is absorptivity. It is same written in here, so you have to read that. Next, since conservation of energy requires all the incident flux to be absorbed, transmitted, and reflected, we have alpha tau r equal to 1. This is the most important concept. Also, Kirchhoff law says same. Or in the case of opaque mineral, where tau is 0, we have alpha plus r equal to 1. What is tau? We read that transmissivity. And opaque material does not transmit light from opaque material, so that tau value is 0 and alpha plus r equal to 1. I think this is sufficient length for this video. We study about Kirchhoff's law and wind displacement law in another video. So thank you so much for watching this video lecture, and tell me that for this subject English language is okay. Otherwise we continue in English as we discuss all the PYQs and concepts in Hindi and English mixture. Okay, so thank you so much for watching this video lecture and very best for your examinations.